now we can continue to see another interesting problem, but maybe a little bit tiring to solve it because there are many cases, but we can solve this problem. This problem is Barkham Mass Olympiad TST, and it asks us to find all natural number n such that there exist the two primes p and q, such that p plus 2 is equal to q twin primes, and at the same time there exists an n such that 2 to the power of n plus p and 2 to the power of n plus q. These two expressions are also primes. So the first thing is that how do we approach this problem? Maybe you see, from this twin prime condition, it's natural for us to consider some, because we know nothing about them, but we only know that there are for numbers p plus 2 and 2n plus p. Sorry, maybe I can change the sequence: p plus 2n and p plus qn plus 2. It means that we need to find some n such that these four numbers are all primes, right? Maybe due to, since we have some equation, maybe we can try modular arithmetic, right? We first look at these two expressions: p plus 2. P plus 2, we may try modular 2 if we see there's some things that it involves too many multiples, but we can get nothing from here. You can have some try. It's we know that it's trivial for p is congruent to p plus 2, and it's similar for other cases. So mod 2 isn't a good choice here. We may try mod 3, which is better, way better than 2, because now we see p and p plus 2, they have different remainder modulo 3, right? And p and p plus 2 cannot be divided by 3 because they are prime, if they are both greater than 3. If they are not 3, for example p isn't 3, then p and p plus 2, since they have different remainder, have to be 1 and 2 mod 3. However, if p plus 2 is equal to 2, then p will be congruent to 0, which it does not suit our condition. So the only possible way is that p is congruent to 2 mod 3, and p plus 2 is naturally congruent to 1. This is the only case that can make p and p plus 2 are both primes. And this is very good because finally we get some meaningful, and at the same time it's a quite beautiful and concise condition, right? You can see here. And using modular 3, we can also get some information from this two expression. We know that p plus 2n should be congruent to p2 plus 2n, since p is congruent to 2, right? And 2n can be rewrite as negative 1 to the power of n mod 3. and the p plus 2 should be a prime, and as a result p has to be at least n cannot be even, right? If n is even, then this expression adds to 3, and it means that this is divisible by 3, and it cannot fit our condition of prime. So n minus n have to congruence 1, congruence to 1 mod 2, right? This indicate that n is an odd number. That's cool. We have some condition here, and at the same time, we can also check for p plus p p plus 2 to the 2 to a power of n plus 2, and similarly we have 4, which is 4 to the power of 4 plus -1 to the power of n mod 3, and we have n is congruent to 1, which means that this congruence is equal to 3, and we know that this is impossible because it implies that 3 is divisible by 3 divides this expression, but in the question asks us to find a prime, and as a result p, we know we suppose that p isn't equal to 3, but here we know that when p isn't equal to 3, there's no solution. So we have a very strong condition, p is 3. Now the problem seems to be much easier, right? Those four primes can be rewrite as 3, 5, 3 plus 2 to the power of n, and 5 plus 2 to the power of n. Now our goal becomes similar and become clear. We want to find n such that these two expressions express primes. How do we approach this problem? We know we simply know that we can still try something about modular 2. Modular 2 is trivial, it will not give us anything meaningful. If we modular 3, we know that here is -1 to this congruence to -1 to the power of n, and this congruence to 2 plus -1 to the power of n. And this does not give us anything, because no matter n is one number, it does not congruence to 0 mod 3, right? So but this expression gives us some meaningful facts. -1 to the power of n cannot be 1, because in that case it will add to 3. As a result, n have to be odd, right? N has to be odd. This condition has to hold. And no other condition. We don't have any other conditions. So in modular arithmetic, to solve this equation, we may look for other modular. We may mod the next prime is 5, right? When we mod 5, 3 we know 2, we can we know that n is an odd number, so we can rewrite n as 2 to the power of n minus 1. And minus 1 is an even number times 2, and this is equal to 4 times 4 to the power of n minus 1 over 2 times 2. And why we want 4 is because 4 is congruent to -1. and this is very very good. So when we mod 5, we have this. And in order to make this should not be congruent to 0, right? So this cannot be 1. This has to be -1. And if this have to be a -1, it means that this n minus 1 over 2 should congruent to 1. This should be an even number, an odd number, sorry, an odd number. It means that n minus 1 over 2 is equal to 2k plus 1, sorry, is equal to, and at the same time we have is equal to 4k plus 2, so as a result n is equal to 4k plus 3, and we got another congruence condition, which is n is congruent to 3 modular 4. We get further detail from looking at modular 5, but we still cannot fix this problem. Our basic assumption is that n should not be infinite number, right? It should at least maybe we can find a few in some small number, but definitely we cannot have infinite n's. So we need to show that for large n, it cannot exist large n that satisfies our condition. So we may further look at modular 7. When we take a look at modular 7, we have modular 5. At the same time, when we didn't talk about when this expression 5 plus 2 to the power of n modular 5, but this is congruent to 2 to the power of n, and it is impossible to be divisible by 5. So nothing, though there's no information here, and we continue. Let's write out these two primes, and we when the first prime modular n modular 7, we know that the 2 to the power of 3 is equal to 8, and it's congruent to 1 more 7, which is a very great condition we can use here. So let's see, when we consider the first prime, this should we can see we can express n as 3k plus r, right? We use this expression with 3 because in using this expression we can have 3 plus 2 to the power of 3k times 2 to the power of r, and 2 to the power of 3k is equal to 1. So we've left with 3 plus 2r, where r is smaller than 3 and greater or equal to 0. And in this case, it gives us that at when modular 7, since this should not be equal to 0, so r should not be equal to 2. R can be 1, or r can be either 0 or 1. So, and yeah, that's how this prime gives us. That's what this prime gives us. And we may look at the second prime, and for the second prime, similarly, we do the similar thing, and this should not be congruent to 0 modular 7. So r should not be 1. Yeah, right. If r is 1, then this expression equals to 7, and it means that the second prime is divisible by 7, so we cannot do that. So based on these two properties, we conclude that that n should be 3k. which means that n is congruent to 0 mod 3. Now we have several constraints on n, right? And we think that if we keep looking for other prime numbers such as modular 11, modular 13, we can have further constraints on n, and finally we find a contradiction that proves that n cannot be large number, right? But till now, we have these two condition, and this condition is included in this condition. So how can this two what how can we kind of uh integrate these two condition into one? We have n is congruent to 3 mod 4, and we have n is congruent to 0 mod 3. We want to find a single condition, right? Maybe we can first write we can first we can first write uh n is congruent to 3 or 7 or 11 or 15. Sorry, we can directly, I mean, we can write n is equal to 4k plus 3, right? And we from the first equation, and we can substitute it into the second. 4k plus 3 is equal to 0 mod n, and it gives us 4k is equal to, this congruent is divisible by 3, right? It implies that 3 divides k, and we can write k as something like 3 3k 3s, right? And as a result, n is equal to 12s plus 3, and it gives us that n is congruent to 3 mod 12. This is how we incorporate the first two conditions into one, and this is very beautiful, right? And if how we can see if it makes something different, mm, we see here 3, we see 3 plus 2 to the power of n, 5 plus 2 to the power of n. If we divide them by, we can try if we can divide them by 12, if it gives us any condition. 3, it is, we can substitute it, and we find that it is congruent to for 12. We know that, oh, maybe modular 12 is not that useful, but we see here n is equal to 12s plus 3. 12s raised to the 2 to the power of 12s. What we think is nice is that from the famous little theorem, we have this congruence, right? Since 13 is exactly a prime, and we have 2 to the power of p minus 1 is congruent to 1 mod p, and when p takes 13, we have this, and this is very beautiful, because in this scenario we can separate 2 to the power of 12s with 2 to the power of 3. 2 to the power of 12s is is congruent to 1 modulus 13. So we can quickly get that this is congruent to 11 mod 13, which is very good because this is 2 plus the first expression, and it means that for the second expression we can do it similarly, and we finally get that it is congruent to 13, which is congruent to 0, which means that 13 is divide 13 divides 5 plus 2 raised to the power of n, and it violates our prime condition. So as a result, n cannot be large number, right? N may be 13, but n cannot be large number. Now we test small numbers for some result. We know that the first two numbers are 3, 5, and the third is 3 plus 2 to the power of n, and the fourth is 5 plus 2 to the power of n. And when n is 1, when n is 0, we may start with n is 0. This is equal to 4, and it's not a prime. N is equal to 1. This is equal to 5, and this is equal to 7, which is great. When n is equal to 2, it adds to 9, and this adds to we know that n should be divisible by 3, and it's obviously it cannot satisfy the condition. When it is equal to 3, this adds to 11, and this adds to 13. We know this divides 13. 13 divides this prime, so this prime has to be 0 or 13 or something like that. So we've got the final condition, final set of solution is this two. So our final condition, final solution is n is either 1 or 3, and we've finished this problem.